Okay, let's just jump right in. Today, we're not just looking at some small tweak to AI hardware. Nope. We are diving into a brand new paper that proposes a completely different way of thinking about computing itself. We're talking about a radical new kind of computer designed specifically for the future of AI. And the headline claim? It's it's just mind-blowing. The authors are talking about a system that could do what today's best GPUs do, but using about 10,000 times less energy. No, that is not a typo. 10,000x. That's 4 orders of magnitude more efficient. And this chart, which is straight out of the paper, really puts it in perspective. This is showing the energy it takes to generate one single image. On the left, you've got a GPU, using around 10 to the minus 5 joules. And on the right, this new thing, the Denoising Thermodynamic Model, or DTM, uses just 10 to the minus 9. That is the 10,000x difference, right there in front of you.
So yeah, that brings us to the big question, right? How on earth is this even possible? A 10,000x improvement in a field where every little gain is usually a huge fight. Well, to get the answer, we've got to first understand the massive problem they're trying to solve. And that problem is a big one. You could even call it a looming crisis. All these incredible foundation models we use, they are built on a mountain of computation that just keeps growing. Every single year, AI data centers are sucking up more and more power, and it's putting a serious strain on our energy grid.
To put a number on it, the paper points to a projection that by 2030, which is not that far away, these data centers could be using 10% of all the energy produced in the entire United States. I mean, you can see how just trying to scale up what we're doing now, it's just not sustainable. So why are we stuck on this path? The paper brings up this really cool idea called the hardware lottery. And the concept is pretty simple. We didn't necessarily pick the best, most efficient way to do AI. We just came up with algorithms that worked really well on the hardware we had lying around, which were GPUs, originally made for playing video games. So we basically won the lottery by accident, but it might have locked us into a system that's, wildly inefficient. To find a better way, these researchers decided to look back at an older but really powerful type of AI called energy-based models, or EBMs. The idea here is actually pretty elegant. The model just learns to assign a low energy score to things that look right, like a real photo of a dog. And it gives a high energy score to things that are just wrong, like a screen full of static. But, of course, there's always a catch. When an EBM learns to model something complex, like all the images on the internet, its energy function turns into what the paper calls a complex, rugged energy landscape. And this is a great way to think about it. Imagine these deep, beautiful valleys represent good data, like a perfect picture of a cat. But to get from one valley to another, you have to climb over these huge, jagged mountains. And trying to navigate that landscape is incredibly difficult and takes a ton of energy. And this gets us to the absolute core of the problem, what the authors call the mixing-expressive tradeoff. Let me break it down. It means the better your model gets at understanding really complex stuff, that's the expressivity, the more rugged and impossible that energy landscape becomes. And that makes it exponentially harder and slower for the model to explore and generate something new. This single trade-off is what killed off earlier attempts to build computers like this. And you can see that trade-off right here. This table shows that as you push for better and better performance from one of these old-school EBMs, the mixing time, which is basically the energy cost, it just explodes. To get a really high-quality image, the cost balloons by 10,000 times. It's a complete dead end. So what do you do when you hit an impossible problem? Well, you change the rules of the game. The huge breakthrough here is that they just stopped trying to model that entire crazy landscape in one giant leap. Instead, they found a way to break the problem down into tiny, manageable pieces. And the solution is this brilliant process called denoising. Here's how it works. You start with pure static, total noise. Then you apply a whole chain of really simple EBMs, one right after another. Each little model has a super easy job. Just clean up the image a tiny bit. And because each step is so simple, its energy landscape is smooth and easy to navigate. So by stringing all these simple steps together, you can go all the way from random noise to a perfect clean picture, and you never have to climb those giant energy mountains. This slide just lays it out perfectly. The old way was like trying to jump from one valley to another, right over a mountain range. Good luck with that. The new way is like taking a series of small, easy steps along a nice, smooth path. One gets stuck and wastes a ton of energy. The other is reliable and incredibly efficient. This is how they completely sidestepped that killer trade-off.
And get this. This is not just some fancy algorithm on a whiteboard. It's an actual blueprint for a real chip. They've proposed a design that only uses standard transistors, no weird exotic materials. It cleverly uses the natural, random jiggling of transistors when they're running on super low power. It's basically turning the universe's background noise into a feature. And the best part? It can be built using the exact same manufacturing processes we already use for all our modern chips.
And that is the absolute key here. The fact that this uses standard technology means this isn't some lab curiosity that's never going to see the light of day. It's a blueprint for a real, commercially viable, scalable solution that could totally upend the economics of AI.
So, looking ahead, the authors aren't saying, hey, throw away all your GPUs. Instead, they're introducing this new idea called hybrid thermodynamic deterministic machine learning. The big idea is to build systems where you have these new, crazy efficient chips handling the stuff they're good at, while good old GPUs handle the rest. It's just about using the right tool for the right job to create a system that's perfectly balanced and optimized. At the end of the day, their whole philosophy is summed up perfectly by this quote from the paper: "The goal is to design computers that respect physical constraints." It's about building hardware that works with the laws of physics to be efficient, instead of just trying to brute force everything and fight against them. And that kind of leaves us with this final, really big thought. For so long now, AI progress has been all about how much energy and money we can throw at the problem. But if a technology like this comes along and makes energy basically a non-issue, what new doors does that open? What could AI really truly become if energy just wasn't the limiting factor anymore?